Welcome to this comprehensive documentation of essential geotechnical engineering laboratory apparatus. Today, we examine 15 tools critical for analyzing soil properties and ensuring structural integrity. Starting with the sieve shaker and sieves, this equipment is vital for grain size distribution analysis in coarse soils. It consists of a nested stack of brass sieves with varying mesh sizes. During operation, the mechanical shaker provides continuous vibration, causing soil particles to fall through the mesh levels until they are retained by a sieve matching their size. Next is the hydrometer. This glass instrument is used for the particle size analysis of fine-grained soils like silt and clay that cannot be sieved effectively. Based on Stokes' law, the hydrometer measures the density of a soil-water suspension over 24 hours, tracking the settling rate of particles to determine their diameter. The Casagrande apparatus is used to determine the liquid limit of soil. It features a polished brass cup, a hard rubber base, and a precise cranking mechanism. As the technician turns the crank, the cup is lifted and dropped. This determines the moisture content at which a soil groove closes after 25 blows. Determining the plastic limit involves the plastic limit set. This simple yet essential kit includes a frosted glass plate, a spatula, and the soil sample. The soil is rolled by hand into thin threads. The plastic limit is reached when the thread crumbles exactly at a diameter of 3 millimeters. The standard Proctor compaction mold is used to find the moisture density relationship. It consists of a heavy, cylindrical steel mold with a detachable collar and a manual hammer. By applying dynamic compaction to soil layers, engineers determine the optimum moisture content required to achieve maximum dry density for construction foundations. The odometer, or consolidometer, measures the settlement of soil under load. The specimen is held in a brass ring between two porous stones within a loading frame. Vertical stress is applied in increments. A dial gauge monitors how the soil compresses as water is squeezed out, simulating long-term building settlement. To measure shear strength, we use the direct shear apparatus. It features a split metal box, a normal load hanger, and a motor-driven horizontal ram. A constant vertical load is applied while the box is pushed horizontally, forcing the soil to fail along a predetermined horizontal plane to find its internal friction. The triaxial shear machine is a sophisticated tool for determining stress-strain relationships. The soil specimen is placed in a transparent Perspex chamber. By controlling both the water pressure around the sample and the axial load from above, engineers can simulate complex underground stress conditions. The constant head permemeter measures the permeability of sandy, coarse soils. It uses a vertical cylinder and a system of piezometer tubes. By maintaining a constant water level in the supply tank, we measure the rate of discharge to calculate the soil's hydraulic conductivity. For fine-grained soils with low permeability, the falling head permeter is preferred. It uses a small diameter standpipe connected to the soil mold. The test monitors the rate at which the water level drops as it slowly permeates through the clay, providing data for drainage and seepage analysis. The California Bearing Ratio, or CBR test, evaluates the strength of subgrade soil for road pavements. It measures the resistance of soil to a penetrating plunger. Surcharge weights are applied to the surface to simulate the weight of pavement. The force required for the plunger to penetrate the soil is then recorded. To find particle density, we use the specific gravity pick. This typically involves a specialized flask, a vacuum pump, and a high-precision balance. By comparing the mass of the soil to the mass of displaced water, the specific gravity is calculated, which is a fundamental property for all soil calculations. The sand replacement cylinder is a field test tool for measuring in situ density. It includes a metal pouring cylinder and an inverted cone mechanism. Technicians excavate a small hole, then use the cylinder to fill it with a known volume of calibrated sand, allowing them to calculate the density of the earth removed. Finally, the unconfined compression tester is used for cohesive soils. This apparatus crushes a freestanding clay cylinder vertically without any lateral support. It provides a fast-paced measurement of shear strength. The test continues until the soil specimen fails, often by shearing or bulging under the axial load. Mastery of these 15 geotechnical tools is the foundation of safe and efficient engineering design. Thank you for joining this laboratory documentation.